In this lecture, we're going to continue with the topic on wave transformations. Radiation stress is defined as the excess flow of momentum due to the presence of wave. As a train of wave moves towards the shoreline, radiation stress increases. And as a result of that, radiation stress actually reaches a maximum just before the breaker point, and produce a maximum set down of the mean water level below the still water level. But after that, when the wave continues to move shoreward, radiation stress reduces due to the energy dissipation at the breaker point, and as a result produces a maximum set up of mean water level above still water level at the shoreline. In this figure, we show the view of the coastal beach and the still water level. Remember that the still water level refers to the situation whereby there is no wave in the sea. Now, if there is wave in the sea, then of course we expect to see the surface of the water fluctuate up and down. When the surface of the water fluctuates up and down, we normally assume that the equilibrium position is still the still water level. However, that is not the case. Because of the radiation stress, actually the mean water level will be below the still water level at the breaker point, meaning to say that the wave actually goes up and down, not about the still water level, but up and down about this mean water level, which is lower than the still water level due to radiation stress effect. And this mean water level eventually actually is higher than the still water level, nearer to the shoreline due to a set up effect because of the reduction in radiation stress. So we will observe wave going up and down about this mean water level all the way to this point, which is the limit of the wave setup. Once the wave reaches this point, it will use its residual energy to wash up the coastline to this wave uprush limit. So this is the mechanics in the swath zone. This figure here again show the zone between the breaker point and the shoreline. This is the beach with a slope of given by this expression, which is the change of water depth d over the distance x. This is the still water line. We have a set down here represented by d prime, which is a negative value because it goes below the still water level, and we have a setup here represented by d double prime, which is a positive value because it goes above the still water line. So due to the set up and the set down, we have the mean water line, which is now in this orientation over the distance L in this surf zone. So the water depth changes and is represented by D at the breaker point. Now, if we look at the geometry of this figure carefully, we will see that the slope of the mean water line, which is this line, is given by a triangle whereby the vertical is d double prime plus the d prime. So d double prime plus the d prime is the vertical of a triangle for this mean water line. Of course, because d prime is a negative value, so we only take the magnitude in order to get the vertical of this triangle for the mean water line, and the horizontal is L. So that is the slope of the mean water line. The slope of the beach is given by d over the distance x. So if we look at the overall, then it's given by this triangle, which is d plus the magnitude of d prime over the distance of L. D plus d prime over L. That is the beach slope. So that is the mean slope of the mean water line. And we have a notation for the slope of the mean water line is written as d prime over dx. Typically, the set up will be larger than the set down. The set down is given by this expression over here. D prime equals to negative 108 times h squared times k over sine hyperbolic of 2kd. Take note that there is a negative. For deep water condition, there is actually no set down, so d prime actually equals to 0. But for shallow water condition, then this equation can be simplified, and it equals to negative h squared over 16d. Here we have the equation for the slope of the mean water line given by an empirical equation, whereby it depends on the beach slope and parameter gamma, where gamma is equals to h times d plus d prime, and typically it takes the value of 0.9. This is based on observations in coastal area around the world, and if we are able to solve the slope of the mean water line, then we can use the geometry in the previous slide to work backward and get what is the wave set up, the d double prime. D prime is calculated using the equation in the previous slide. We take note that the equation is derived and is valid for normal wave incidence only, or the normal component of an oblique wave that approaches the sea at an angle. And the equation is also only valid for small amplitude wave theory. And of course, in this case, we have to be careful when we apply it in the near shore zone, because the near shore zone, the waves are less likely to remain small amplitude because of the asymmetry that develop. However, this is a simple approximation of the wave set up and wave set down in the coastal region. Now, please keep the goal and try to solve this problem without looking at the solution, and we will discuss this in our online session.